Okay, so formula sheets. Okay, so what I'll do for the quiz is I will put up a slide with the most important formulas. It's going to be like a photo that I've taken from the book. We're going to have like our lecture session, so you can all be on here, right? I'm going to be silent, but just in case there are questions or issues. And I will put up a slide like this, but with formulas. So you can always like switch tabs, look at the formulas, and then go back to the quiz. Okay, make sure to be on time for the quiz, by the way. The quiz is going to start at 11 a.m. sharp, and you will only have a few minutes to access the link. So if you're too late, then you miss the quiz. So be on time. You can use a calculator for the quiz. No other resources, please. Don't use Excel. Don't look things up online. Hopefully you know that. Only a calculator and the formulas that I provide. And it should be, I've tried not to make the quiz too hard, right? Because of this issue again. I don't want to hurt you guys too much, so it should be relatively easy if you know what you're doing. Okay? Okay, so let me just get started since we've spent too much time on this. Badr, go ahead.
Small question. Is the quiz gonna be the same level as the homework?
My philosophy is generally that the homeworks are harder than the quizzes, because with the homeworks you have more time. It's practice, right? You're in a relaxed environment. So I will try. Of course, that's not always how things turn out, because my experience is different from yours. You're still learning the material for the first time. So I will try to always make the homework slightly easier than the quizzes. That's sort of my philosophy in general. Like homeworks, I challenge you. I want you to practice maybe, but quizzes, like, they're just to test whether you know one or two key concepts. Okay. So it's not going to be harder than the homework, is what I'm saying. Like it's going to be at the same level, probably easier, and should be easier. I tried to design it to make it easier. So, okay. So this chapter, as I said, is about understanding money management, right? And so if you look back at the course objectives in the syllabus, this chapter is actually related to, well, it hits multiple objectives. But one of them, if you remember, if you've read the syllabus, and I encourage you to read the syllabus, I mean, that's what Snoop Dogg told you to do, right? Read the syllabus. One of the main course objectives is to like gain some understanding into how to make good economic decisions in your personal life as well. And so we'll see in this chapter, like we're going to discuss maybe like things that are related to credit cards, as well as things that are related to auto loans, like buying a car, right? Getting a loan for purchasing a car. And so this chapter also helps you personally, as well as just being of interest in general for engineering economics. Okay. So here are the objectives of this chapter. We're going to talk about something called the nominal interest rate, and also something called the effective interest rate, and we're going to distinguish between them. If you remember from last chapter, we were talking about I, right, being the interest rate, and it was always equal to some percentage, some value. And so now we're going to zoom in on this I a little bit. In fact, I think in chapter 3 and chapter 4, we're going to zoom in on this I a little bit more to understand what it is exactly and what different types of I's there are. And so that's what nominal and effective interest rates are. So there are different types of interest rates. And we'll see how to convert or how to go from one to the other, right, today, actually. And related to that is the term or the phrase annual percentage rate, APR. And so this is a very common phrase, and we're going to see examples of that. And it's really, APR is very related to nominal interest rate. And also APY, which is annual percentage yield, that's related, or actually is the same as the effective interest rate. And so these terms are what I'm talking about when I say it's going to be useful for you in your personal life, because this is a very common term in any loan or any credit that you need to take. We're gonna see or discuss how to compute effective interest rates, right, for a given time period. And again, this may not mean anything to you right now, but we'll see as we go along and we see examples. Hopefully, when you come back to the slide, you will see, oh, I understand these things now. And we're going to talk about something that's called continuous compounding of interest, and we're going to develop a formula for that. Okay, at the moment, maybe you've heard of this before, maybe you haven't, that's fine. And we're going to understand or see how some loans, right, some debts, how they can be managed, right? Okay, so these are the objectives of this chapter. So some of the issues to consider, if you remember in chapter 2, I give you a cash flow, right? And I give you, for example, years. Those are your interest periods, right? And I have a payment at each year. And then I tell you that the interest rate I is, let's say, 8% per year, or 8% compounded annually. Okay? And so notice here that this is given per year. This is also given per year, right? These are years, for example, in this cash flow diagram. So that made life easy for us, and we know how to deal with these types of cash flows. We've seen this in chapter 2. So in this chapter, we're going to generalize this a little bit, and we're going to ask the question, what about if these payments occur more frequently than once a year? So let's say, for example, I add a payment, or maybe instead of adding a payment, I change these, right? Instead of these being years, these are now 6 month periods. So this thing here is a year, right? But I have 2 payments in that year, one at the end of the first half and one at the end of the second half. But the interest rate is given per year. So how do I go about this, right? This is the question that we're trying to answer in this chapter. How do I do my computations? Because the interest rate is not sort of in the same units as my payments. So I need to do something. I need to do some conversion in order to make things have the same units, and then I can proceed normally with my calculations, right? And so this says if the payments occur more frequently, how do you do your computations? But also if the interest period is not annual, let's say my payments are annual. So let's go back to the example of these payments being every year, right? 1, 2, 3, 4. These are 1, 2, 3, 4 years. But my interest is given, let's say, per month. Again, this is not really standard, so I need to do something to convert my interest rate, for example, to be annual, and then I can proceed with the formulas that we've had before. Okay? And then these 2 questions are related to the last 2 objectives about commercial loans and about debt. So these are the questions that we're going to try to answer in this chapter. So this is just generalizing what we've already covered. And so to start with, I told you we're going to see the difference between nominal and effective interest rates. And so I'll give you the definitions here, but this may not become clear at this point. Hopefully with examples, this will become a little bit more and more clear. As I was refreshing, actually just reading the book and reading the slides, it was not clear to me at first. But when I saw examples, it became a little bit more natural. So it's fine if I can't get the point across to you guys right now, you don't get it. It's fine as long as you understand the examples. And hopefully then when you read this, it will make a lot more sense. So the nominal interest rate, so nominal in Arabic is ismi, right? It's something that's quoted, it's given to you. Just so nominal, I think, like comes from name, I guess, maybe, or they come from the same root, right? So that's why it's ismi. So it comes from name. And so this is what the bank quotes you. So if you're borrowing money, the bank is actually going to quote you a nominal interest rate. So it's the interest rate that's quoted from the bank, and it's always going to be based on an annual period. So this is something like the bank says your interest rate is 8% per year, right? So 8% here is the nominal interest rate. And so that's fine, but let's look at the other one. So the other one is the effective interest rate. So this is the actual interest that you pay in a year or any other time period. And so because I have 2 types, you might immediately think that there's a difference between these 2, and of course there is, right? So this is what you're quoted, this is what the bank gives you. However, what you end up paying can be different from this number, depending on how frequently you apply the interest. So maybe the bank tells you it's 8% per year, but remember that's ismi, right? That's nominal. But the effective or interest rate, which is fi'li, is a little bit more than this 8%. For example, it can be you end up paying like 8.3%, for example, in a year. Why is that? Because even though the bank tells you it's 8% per year, the bank may be applying the interest every month. So this is a little bit weird, and it was not very natural to me. And I'm not sure why banks do this. Maybe it's like a legal requirement. Maybe there's a good economic reason, or maybe they just want to confuse us in order to take our money, right? And so they will tell you it's 8% per year, but really what you end up paying is a little bit more. And they're always required, I think, to give you a figure that's based on an annual period, right? And this is annual, like how much you end up paying in a year, but it's computed a little bit differently, and we'll see the difference between these 2 and how to go from one to the other. But just know that we have these 2 types right now. And so let's begin to dissect and see what's happening, right? So the bank is going to tell you, right, it's going to give you this phrase. So if you're borrowing a loan, let's say, you're taking out money, the bank is going to tell you the interest rate is 18% compounded monthly, right? And so notice in the previous chapter, what we've normally done is I tell you it's 18% per year, or it's 18% compounded annually or yearly, right? In this case, it's a little bit different. It's 18% compounded monthly. I've changed the units into months. Not only that, but this 18% is actually nominal. What that means is this 18% is an annual figure. So this is like 18% per year, but the compounding is done monthly, right? This is what this phrase means, okay? And so we'll see again examples, and this will become clear. Like, why is one, like I'm saying here it's yearly, but then I'm saying it's monthly. It may be a little bit confusing, but we'll see. Hopefully you will get familiar with this when we see examples, right? And so the nominal interest rate, the annual figure that they quote you, is also called annual percentage rate, APR. And this is very, very common in loans and credit cards. If you haven't like seen this already, you will see it if you get a credit card, for example. If you look at the agreement form, you will see that there's an APR. In fact, and maybe if I say it in Arabic, maybe it will ring a bell for some of you. Annual percentage rate would be معدل النسبة السنوي, right? And so this is a very common term in almost all of your transactions with the bank. And so that's where this thing is useful, right? And notice here, this monthly, this red part here, is actually the interest period. So this represents how frequently you apply the interest. So compounded monthly means this 18%, the nominal rate, I'm actually applying it every month, right? And so let's see what APR is. So I actually pulled up, I've like took some screenshots for you guys. And so this is from Chase, which is a big US bank. And this is actually a credit card that I used to have in the States. And so if you look here, we look at all the benefits and all the stuff like that. But look here, you see here, this box, it says APR, right? So this is the nominal interest rate on this card, which ranges from like 16% to 23%. And they say it's variable. It's a variable APR, meaning it can change with time, like from year to year. And also the way they determine this is like based on your credit history, like how well you are as a borrower of money. And then they will assign you like a value in this range. For example, I may get, if I'm a good borrower, I may get a lower interest rate. So I may have, let's say 16%, but maybe someone else who's not that trustworthy, they may assign an APR of 21%, which is higher. That means they have to pay more interest if they're late, right? And this is not just the case with US banks. So also here, SAB, right? I pulled up their credit cards, and they have this nice comparison between cards. And if you look down here, you see the same thing. The annual percentage rate, 26, ranges all the way up to 28%, or 28.5, 28.6, or 7%, right? And so this is very common, as I said, both here and in the US and pretty much in all countries, right? So this term, hopefully you're going to be familiar with this starting today. If you're not, and then it becomes useful for you later on, okay? So now we start to actually look at the numbers, and let's fully understand what's going on here. So I tell you it's 18%, but I said this is an annual figure, but the interest is compounded monthly. So what does this really mean? So what it means is I'm applying the interest, right? This part here says I'm applying the interest every month. So in a year, right, because this is given per year, right? In a year, I'm applying the interest 12 times. So the number of interest periods that I have in a year, or n, as we've had before, is equal to 12. Okay. Now, how do I go from a nominal interest rate to an effective interest rate? And so if I'm given that the 18% is the nominal interest rate per year, the way they do it, and this is where it gets confusing, is that they just divide by 12, right? I have 12 months, so if I want to find the interest rate per month, I just take the 18 and I divide it by 12, and it gives you 1.5%. Now, some of you may already notice that this is kind of a weird operation. Like, you're taking a percentage, you're dividing by a number. Is this mathematically accurate? And the answer is not really. And that's where the effective interest rate comes into play. And so we're going to see an example of how the effective interest rate, actually, because you're applying 1.5% every month for 12 months, you end up with something over the course of a year that is different from your 18%. In fact, a little bit higher than your 18%. So again, I have no idea why they do this, why they quote something and then you end up paying a little bit more than what you're quoted. Just quote me the thing that I'm supposed to be paying. But it is what it is. And unfortunately, we're going to have to deal with this. Okay? In words, what this means is that the bank is going to charge you 1.5% interest each month on your unpaid balance. So if you have a credit card and you're expected to pay $200, but you only pay $150, so that remaining $50 is your unpaid balance, the bank is going to charge you 1.5% interest every month on that, okay? And that amounts to an 18% nominal interest rate, which is an 18% APR, Okay, so hopefully you see you're starting to see the connections between these things, and we'll see more and more examples. As promised, so here's the first example. Let's suppose you invest one single dollar for 1 year at, and then you see here this phrase that I was given before, 18% compounded monthly. How much interest would you earn? Okay, so let's look at a picture just to see what's happening. So this 18%, remember, is based on an annual, like is an annual number. So I give you the 18%, and that's per year. By dividing by 12, I can find the interest rate per month, which we've done before, which is 1.5%. Now, if I want to find the future value of my $1, what do I need to do here? Remember, the interest is going to be applied every month. Yes, Mohammed?
So this is compound interest, so we can use the formula over the 12, so n equal 12 maybe.
Good. Okay, yes. So we use the n equal 12 in this formula. Why? Because I have 12 interest periods. I'm compounding 12 times, right? What about I? Which I should I use?
I think the 1.5%, not the 18%.
Exactly. Yes, because it matches with the months, right? So that hopefully that makes sense to all of you, right? So I use the 1.5%, not the 18%. Okay. So hopefully that's what. Well, someone else had their hand raised. Hopefully that's the same thing that they were going to say. And so you see here, I take my $1, right? We use the formula, compound interest. I mean, it says here compounded, but even if I didn't say that, I mean, it should be clear, right? And 1 plus I to the power n. N is 12 because I'm applying the interest every month. And I is the interest rate per month. They match, right? And so I plug in my I, which is 1.5%, and I get this is the amount that I'm going to have after or at the end of the year. Now, what do you notice? So this is the amount that I'm going to have after the end of the year. How much interest did my $1 earn at the end of the year? Yes, Mazen?
About 19.56%.
Exactly. Now, further, you notice that this number is different from this 18%. It's a little bit higher. You actually earned more effectively, even though the quoted thing was 18%. And the reason is because, I mean, they divide here by 12, and that's how they compute it, which is a very weird way of doing things. Like, they don't compute the actual interest that you earn. It's just, you just scale the percentage, which is not accurate. And so that's where this discrepancy or this difference comes in, right, between the effective. So this here, we're going to see this later. This is the effective annual interest rate, right? So effective, I'm just going to write it like F for effective, annual. So this is how much interest you're really earning over the course of the year, even though you're only quoted the nominal of 18%. Okay? So what is the relationship between the nominal and the effective interest rate? So the nominal, I've already told you, is given on a yearly basis, and then we compute the effective interest rate per month, right, the 1.5%, and then we compute the actual interest that is earned over the course of the year. So this is what the picture looks like. And we started with the phrase, it's 18% compounded monthly, right? So that's what this picture is representing. This is equivalent to, as we found out, if you divide the 18 by 12, it's 1.5% per month applied for 12 months, right? So we're converting, we're going from here to here. And then as we actually found out in the example, if I were to find the effective annual interest rate, what I'm really paying over the course of the year, by taking into account how frequently the interest is compounded, I end up with this 19.56% compounded annually. So notice here I changed from monthly to annually because I found this I sub A, which is the effective annual interest rate. Effective annual interest rate. Okay? Now we're going to put this into a formula, right? So hopefully the picture is a little bit clear now, and we're going to see even more examples later on. So let's see how we can compute this I sub A, right? The effective annual interest rate, if we're given a nominal interest rate. And so that's what this slide here tells you. So first of all, notice that the effective annual interest rate is also known as API. I actually didn't write it here, which is unfortunate, but this stands for annual percentage yield. It's in the objective slides. If you miss it, it's going to be in the second slide, annual percentage yield, right? So this is the effective annual interest rate. It's just another name for it. There was a question.
Sorry, by mistake, I raised the hand.
Oh, okay. All right, so let's see what's going on in this formula. So first of all, I'm given R. So what is R? R is the nominal interest rate per year. So in our previous example, that was the 18%. So I'm just going to write it so you can make connections, right? And then if you remember, we divided to find the interest rate per month. And so you divided by 12, which is the number of months. But really, you're dividing by the number of interest periods that you have per year. I could have done something different. I could have told you that the interest rate, for example, is 18% compounded quarterly, right? So you apply the interest every quarter. And so in that case, you're going to divide by 4 because you have 4 quarters in a year. Okay? And then I add 1, right, like the formula. And then I take this all to the power m. So if I divide by 12 here in the previous example, I get my 1.5, right? I add 1, and then I take it to the power 12. Why? Because I have 12 months that 12 interest periods in a year, right? So number of interest periods per year. Okay? Minus 1. This gives me the interest rate, the effective interest rate. Effective annual, so this A here is for annual, the effective annual interest rate. So if I'm given a nominal, I can plug in this formula and I find my effective annual interest rate. Now here's a question for you guys. Can the effective interest rate be the same as the nominal interest rate? Who was that? Yes, Muhammad?
When m is equal to 1.
Yes. So, I mean, mathematically speaking, when m is equal to 1, of course, if you just do the math, you will see that I sub A is equal to R. Does this remind you of anything like maybe in words instead of just saying when m is equal to 1? Or maybe I'll just tell you since I can't really phrase it into a question. What happened in chapter 2? So you may be asking, like, now I have 2 different types of interest. Well, chapter 2, I didn't know this. Like, I was just plugging in the formula. So what happened? So what happened actually is it's in a way exactly what Muhammad just said. You had, as I've drawn before, you had your interest periods are years, but you only had 1 interest period in every year, right? So the payments and then the interest rate were all sort of in the same units. So this is 8%, for example, per year, compounded annually, right? And so because they're in the same units, you're applying the interest 1 time every year, and so m is equal to 1. And so really, the effective is equal to the nominal. And so that's the case of chapter 2. We just had them equal, and so now we're generalizing and we're seeing what happens when they're different. Okay? So let's see. Oh, by the way, this fraction here, this R over M, so 18 divided by 12, which is 1.5, that's the effective interest rate per interest period. So that's known as I. So there's no sub A there, right? So that's 1.5% per month is the effective interest rate per month. Okay, so just remember that. So here's an example. So I'm changing things up a little bit. So I'm telling you the interest rate is 9% compounded quarterly, right? So every quarter of a year for $10,000 for a $10,000 investment. Okay, and so if you follow along, like if you do it step by step, you take the first quarter, you're going to take your 10,000 and you're going to apply the interest rate. How much is the interest rate? Well, I have 9% per year. I need to convert it into a quarter, so I'm just going to divide because this is nominal. So I divide to get the effective per quarter, and it turns out that's 2.25%. So I take my base amount, I apply the interest rate, I get an extra $225. I move that to the next quarter, and then I do the same thing, right? I move step by step, applying interest each time, and you notice that we get $10,000, $10,930.83 after 1 year. So now let's use the formula really quick and see if we get the same answer. Right, so here's the formula. I actually had like plans to actually write it out, but I don't want to like spend too much time on this. So if you look at the formula, you're going to take R, which is 9%, right? And you're going to divide it. So you're going to do R divided by M, right? So M is 4. So M here is 4. So I'm kind of sketching things out. This is not going to be like, I'm not actually writing the solution in full, right? And so you divide your 9 by 4, you get the 2.25%, right? And then you're going to add the 1. And you're going to take it to the power 4, right? And so this is going to be 4 here. This is going to be 0.09. And you can do the math, right? And then you subtract 1. Now you can compute this. And what you're actually going to get is you're going to get, I think, so let me see if I can do it in the calculator real quickly, because I don't have the answer. I should have just wrote it in my notes. So if you divide by 4, you add 1, take it to the power 4, subtract 1. Okay, so what you get is actually that I sub A is 0.093. or 9.3%. Okay? And if you look back here, if you take your 10,000, you apply this effective annual interest rate, you're going to get exactly, this value at the end. So now you can take this I sub A and you can plug it in the formula, right? So P here is 10,000, 1 plus I sub A to the power n, where n is 1. So n here is 1. Because this is already annual, and I want to find the balance that I have. If I start with 10,000, how much do I have at the end of the year? So now this is in years, this is in years. I have 1 year. I can plug in, and you're supposed to get this same $10,000, 10,930 that we've gotten here, right? Of course, if you would have applied just 9%, you're going to get a very different answer and one that is incorrect. You see here the difference. So this is how much you actually pay. Okay. So this is a table that's summarizing these rates. So here we have the nominal rates, right? And here we have the effective rates depending on how frequently you compound. So notice that if you're compounding annually, meaning you're only applying the interest one time every year, these two things are the same. So that's the case when m equals 1, as Muhammad said, right? So that's this column here. But here, as you start to apply the interest more and more frequently, the number that you get, for example, you see in this case, can be very different sometimes from the percentage that the bank actually quotes you. So I guess in a way we're teaching you how to be smart and not just use this percentage when you're computing things. If the bank tells you this, say, okay, how frequently are you really applying the interest? Let them tell you, and then you can actually compute more accurately what's happening, right? And by the way, you see the 9.31% here. So this is if we're compounding quarterly, as in the example, 9% is the nominal. I actually have the solution here, which I didn't realize. Okay. So now, let's generalize this a little bit more. So before, in the formula, what I had is a payment period of a year. The interest period, however, how frequently I apply the interest can be a little bit different. It can be a month, it can be a quarter, as we saw in the examples. What about, can I generalize this a little bit more so that my payment period can be anything? And so regardless of whether or not my payment period is a year, or if it's like in this example, it's 3 months. So I deposit money, let's say every 3 months, but my interest period is per month. The compounding is done monthly. Can I generalize my previous formula for this case? I notice here what happens is that I would need basically to compute the effective interest period. Now it's not annual, right? It's not I sub A because it's going to be on a 3-month scale. It's going to be I. It's going to be an effective interest rate per quarter. And so here's the picture, right? You need somehow to convert this interest period, which is given per month, you need to convert it into a per quarter interest. So effective interest rate per payment period, which is per quarter in this case. And so the formula actually looks very similar to what we had before. It's just a little bit more general. And I'm not sure like if using the formula is helpful. If you get the concept, you can do it even without using a formula. So let's see what's going on here. So by the way, there are 2 cases to consider. There's a case where we have discrete compounding, and then there's a case where we have continuous compounding. And we're going to see continuous in a little bit. And if you remember, continuous compounding was in the objective slide. So we're going to see what that term means. So in the case of discrete compounding, it's very similar to before, except now what happens is my m has changed to the c times k. And so let's look at what k is and what c is. So k is the number of payment periods that I have per year. And C is the number of interest periods that I have per payment period. And I think, I mean, it may be difficult to follow. Once I show you a picture, this will become a little bit clearer. Okay, but notice here, of course, you're dividing by C times K, but you're raising it to the power C, where C is just the number of interest periods. So this is how much or how many times you apply the interest. Okay, and so we're going to see examples. I don't think you really need to memorize this formula. You can do it, like, if you just understand it, you can just do it without figuring out what C is, what K is. Although maybe it's better to write it to get partial credit if you mess up somewhere, right? And so let's see an example. So I tell you that the interest rate, or the bank tells you that the interest rate is 12% compounded monthly, okay? So I'm applying the interest every month. If you want to figure out what K is and what C is, so C stands for compounding, so C is the number of compounding periods. So in a quarter, you have 3 months. So your payment period is actually a quarter in this case. That's actually given, I guess. It's not something you can deduce from here, right? You're given that you pay or you make deposit every quarter. And so that gives you K. K is the number of payment periods, how many times you deposit per year. So because it's quarters, I deposit 4 times, for example. Now, how many times is the interest applied? So that's C. And per quarter, the interest is only going to be applied 3 times, right? Because why? Because my interest is compounded monthly, right? But my payment period is a quarter. And so there are 3 months in a quarter, therefore C is equal to 3. And what I need to find is the effective interest rate per quarter, and then I can actually generalize that and find the effective annual interest rate. So I'm converting my interest rate to per quarter first and then per year. And so this is a picture that I was telling you guys about. So this is in a year, what's happening. I have 4 quarters, so I make 4 payments. But the interest is applied according to these small blocks here. So it's applied 1 time every month. And so I need to figure out for each payment period, for each deposit, how much interest is it really earning, right? That's this first part here. Well, if I plug in the formula, right? So let me erase the pen so you can see the numbers in the picture. So if I apply the formula, right? So I take my annual nominal rate, which is 12%. I divide by C times K. Well, C is 3, K is 4, so I divide by 12. So I'm effectively finding the interest rate per month, which is 1%, right? 12 divided by 12 is 1%. But then I need to raise it to the power of C, where C is the number of compounding periods per payment period. And so notice here I have 3 compounding periods in this first payment period and in every one after that. So I'm going to raise it to the power of 3. And then, of course, I subtract 1 to find the actual interest rate, and I get 3.03%. Okay, so that's per quarter. Now can I find the annual interest, the effective annual interest rate? Well, I can do the same thing, except instead of raising it to the power of 3, I can raise it to the power of 12, right? Because now I need to scale it up or to find the effective rate for all of these little cubes, right? So I raised it to the power 12 instead of just to the power 3. Another way I could have done that is the following. I could have taken this effective interest rate per quarter, and then I raise it to the power 4, because there are 4 quarters in a year, and that gives me the same answer, right? And so you could do it either way. Here's another example. So let's suppose you're making quarterly deposits. So your payment period, your deposits are every quarter, and you're putting it into a savings account that gives you 8% compounded monthly. What is the effective interest rate per quarter, and what is the effective interest rate per year? So again, this is very similar, so I'm just going to show you the solution real quick. So you take your annual rate, you divide by 12, right, which is C times K, or just you divide it to get the monthly value, and then you raise it to the power of however many times you apply the interest in a given payment period. And so here my payment periods are quarters. I have 3 months, so I raise it to the power of 3. And that's my effective interest rate per quarter. And I could do a similar thing to find it per year. I can either take this thing here and raise it to the power 12 instead of 3, or I can just take the value that I found here, like we did before, and raise it to the power 4, because I have 4 quarters in a year. Okay, let's look at the case of continuous compounding. And so this is kind of interesting, but it's not realistic. It just gives us a mathematical limit on how much interest we can earn in a given time period, okay? So what is continuous compounding? So this is the formula that I've had before, right? That I've showed you and that we've been working with CK, and then we raise it to the power C. And so CK is the number of compounding periods per year. We've already seen that. The case of continuous compounding means that C goes to infinity. And what that really means is that instead of applying, so you can think of it like this. You're applying your interest annually, and then you're applying it a little bit more if you do it 2 times a year. You're applying it more if you do it like each quarter, and then you can move all the way to applying the interest daily. But then you can think about, what if I just apply the interest to the money as soon as I earn it? Right? So that's it's not realistic, but it's mathematically fine. And that's the case where C goes to infinity. So you're applying the interest in a payment period an infinite number of times, which is kind of crazy to think about. And so I can find this actually from the formula that I had before. Right? So if I take the limit as C goes to infinity, what happens is this is a limit that you guys should be familiar with, and if you're not, I'm going to show you what it is. So first of all, the limit, of course, you can take the limit of the first part minus the limit of the second part. The limit of the second part is just going to be 1, right, minus 1. The limit of the first part is actually, if you remember from calculus, it's actually e to the whatever's written here. So here, what I can do, let's look at here first. So you have x going to infinity, and then you have 1 plus y over x. So x is down here, and then I have a y up here. And I'm raising it to the power x, right? So the x is here, and here, and here. Okay, so here I have a c. I have a c times k, and then I have a c. But of course, I mean, this k, I can write it up here if I wanted to. That's completely fine. And so now I have something that looks like the standard form. This limit is equal to e to the y, right? And so here I have e to the r divided by k. So that's what my limit is, and then minus 1. And so that's the expression that you see here. So this is mathematically a limit, right? An upper bound on how much interest you can earn, assuming you can apply the interest an infinite number of times. This doesn't happen in practice. It's not realistic, but it's mathematically useful, I guess. Now, can I take that and find the annual effective interest rate? And the answer is yes. If you remember from before, k, well, let me remember. So k is the number of payment periods per year. Well, if I'm going to find the annual effective interest rate, k is going to be equal to 1 because I only have one payment per year, right? That's how many times I'm going to apply. This is equals. That's how many times I'm going to apply the interest in a year. So if you set k equal to 1, you get e to the r minus 1. So this is the annual effective interest rate in the case of continuous compounding. Okay? So let's see some more examples so you get used to this concept a little bit more and more. And actually, we're going to be looking at the same example, but we're going to change the interest period. All right, so we're going to see what happens as you make the interest more frequent, basically. So here you're given that your payment period is a quarter for deposits, for example, a year. The interest period is also a quarter. So actually, this case is nice because they're both the same, right? And you're given your R, the nominal. Remember, the nominal is always per year, so you're given 8% per year. And of course, you can find, so you have 4 payment periods per year because you have 4 quarters in a year. And you're only applying the interest once every payment period because they match. So when they match, when your interest and payment periods match, C is always going to be equal to 1. So remember that because that's going to be useful. How can I solve this? Well, I'll just plug in the formula. This is a discrete case, right? There's no continuous compounding or infinite number of, right? C is equal to 1, not infinity. And so I use the formula for that. What do I need to do? I need to take my 8%. I divide it by 4, which is the number of quarters that I have. And then I raise it to the power 1 because I'm only applying the interest one time in that quarter. And I get 2% per quarter, which is just 8 divided by 4, really, right? Because they match, it's very, very nice and easy. Now let's see what happens if I change this interest period from quarterly to monthly. So you see here the picture changed. Whereas before I had one interest period for my entire deposit, just one time. Here I'm applying the interest 3 times for this one deposit, right? So now K stays the same because I'm still making 4 deposits, but C changes because now I have 3 interest periods in each quarter. And so how's the formula going to change? Well, I replace C, instead of 1, I replace it by 3, and I raise to the power 3. And I get a number that's slightly higher. So from 2, it went to 2.013%. And we can keep going. What about if I do an interest period that is weekly? And so, well, I need to find C, right? So C, again, is the how many weeks I have in a quarter. And so I know that there are 52 weeks in a year. And if you don't know, you should memorize this, right? 52 weeks in a year. And then if I divide it by 4, I'm going to get 13. Right? For quarters, I get 13 interest periods per quarter. I plug in the formula. Again, I substitute as necessary, and I get my answer, which is, again, a little bit higher. Which makes sense, right? As I'm applying the interest more frequently, my money brings me more money. And so the rate actually goes up. I'm earning more money if I'm depositing. What about continuously? Well, notice here that this now has become one contiguous block, right? There are infinite number of interest periods here. And so now there's no C, right? Because C is infinity, right? I only, if you remember, even in the formula, it was e to the r divided by k. So I only care about k, which is going to be 4 still. I have r, which is 8%, so I can just plug in, and I find that it's 2.02%, which is a little bit higher than the one I had before. And this is an upper bound. Like, this is the best you can do, right? Because it's infinite. And so here's the summary. Like, here's what the numbers look like. So if you compound quarterly, monthly, weekly, continuously, as your compounding period gets smaller, that means you're applying the interest more and more frequently, and that means your rate actually goes up. Okay, so now let's look at a bunch of practice problems. So here's where APR, I mean, you see the word APR is comes into play. And so we're talking about credit cards in this example. So suppose the credit card computes the interest based on the following rate. It tells you that the rate is 12.5% APR compounded monthly. So the nominal is 12.5%, but the compounding is done monthly, as is normal with credit cards. So it's asking you what is the monthly interest rate and what is the annual effective interest rate. And then it's asking another question, which is if, let's say, you have a balance on the card that you haven't paid worth $2,000, and you're not paying this balance for 2 months, how much would the balance be 2 months from now, right? So if you think about it, this is a future value 2 months from now. And so let's see how to do this. So first, I need to find the monthly interest rate. How do I do that? Maybe you guys can help me with this.
Divide by 12. Divide the interest
Exactly.
by 12.
Yes, that's all you need to do. All right. So if you remember, I told you before, I is going to be equal to R divided by M, which we may have seen in the previous slide. So you have R, right? And then you have M, which is the number of interest periods, which is just 12. So you divide and you get the monthly rate. To convert this into an annual effective interest rate, what do I need to do?
One plus I to the power of 12.
Exactly. Yeah, I think I heard 12. I'm not sure if it was 12 or 10, but hopefully you said 12. But exactly, that's what this is. 1 plus I, right? 1 plus R divided by M, for example, or R divided by CK, doesn't matter. CK is equal to M, to the power of how many times you apply the interest, which is in this case is going to be 12 because you're applying the interest monthly. And you find this percentage. Again, if you look at the APR was 12.5%, so this is higher. So this is how much you actually pay. Now, to find the outstanding balance, I've already gave you a hint. This is really a future payment. So now you use the formulas that we've been using in the previous chapter. You take your $2,000 balance, and you need to find the balance after 2 months. But now you use the interest rate that corresponds to the months, right? Because you want these to match. And you compute the formula, you compute the value, and you find that it's this thing here, down here. Mazen?
Yes, doctor. In a question like this, doctor, outstanding balance. At first, I thought I'd use the effective monthly income in this case because it's more realistic. So,
well, this is using the effective, right? So this is like this here. This is effective. It's effective per month.
Oh, okay. So it's given before.
Well, you're given the nominal, right? But then when you divide by 12, you're actually finding the effective interest rate per month at first. So this I equals R divided by M. This is actually effective. And if I go back, like just to make sure everybody also is following along. So if I go back, where was it? Yeah, so see here? So this is the first formula that we've seen, R divided by M. This part here is the effective interest rate per interest period, I. So if you're just dividing your 12.5 by 12, you're finding the effective per month. And that one is the one you use to find the outstanding balance, to find how much it will be after 2 months. Right? So you're using this one here.
No, thank you. It's clear now.
Okay, good. All right, so this is another example. I'm going to skip over this because it's very similar. You can do this in your own time. Again, it's the same sort of concept. And so now we come back to the question of how do I compute stuff, right? And so now I know the difference between a nominal and an effective interest rate, how much I'm actually paying versus how much the bank tells me I'm supposed to pay. How do I use the formulas that I've learned in Chapter 2? And the answer is you follow generally these 3 steps. You need to first identify the payment period, how many payments you're making, and then you need to identify how frequently the interest is applied, the interest period, right? And these may not match. Sometimes they do, sometimes they don't. But then, regardless of whether or not they match, I need to find the effective interest rate, right? That covers my payment period, and then I can use that in the calculations. And we've already seen this in the previous example. For like, you find the effective, and then you use that to actually compute the actual interest that you're earning, or that you have to pay. And so there are 2 cases, right? As I said before, these things may match, may coincide which is the case where an example of which is the case we had in chapter 2, where this was annual and this was annual. So that's the case where the payment periods and the compounding periods coincide. And in that case, C is going to be equal to 1. Okay, we've already seen this. We've said this before. The other case is when they're actually different from each other. And then you need to do some conversion in order to make sure that things have the same units, right? And so they divide this into 2 cases. However, I'm not sure why they do this. Again, it seems useless to me because you can follow generally the same steps in either approach. But I'll just follow what the book says. So let's take the first case where your payment periods and your compounding periods coincide. So as we said, C is going to be equal to 1. And so here they give you like the steps that you need to walk yourself through in order to solve a problem that has interest calculations, right? So first you need to identify, or you need to compute what M is. So M is equal to CK, as we've seen before. Now, if the payment periods and compounding periods are the same, then C is equal to 1 and M is equal to K, right? So you just need to find M. That's the first step. The second step is you take your R, you divide by M, and you see here, I think Mazen, you asked the question. You see here, I equals R divided by M. So this is actually the effective interest rate per payment period. And then you need to find out how many times you're applying the interest, just total, right, over a number of years maybe. And so you take your M, which is how many times, how many compounding periods you have in a year, you multiply by the number of years, for example, and you find your N. And then you use the appropriate I, which is here, and the appropriate N in the formulas that we've seen before in chapter 2. And so let's see an example. I mean, this is really not saying anything new. We've already seen an example where we kind of did this. This is just laying things out in steps. So here's an example where you have an auto loan, you're trying to get a car and you get it financed, let's say, from a bank. So the bank is going to say, I'll give you a loan at 8.5% annual percentage rate, so 8.5% APR, right? And the loan is going to be for 48 months. So you're going to make payments, right, every month. And so this tells you what your payment period is, if you notice. And then, of course, this is an ad, so there's stuff here that we could skip, all ready for delivery, blah, blah, blah. So this is the price of the car. This is how much you're going to pay. But you need to add some things, right? You need to add sales tax, which is 4%, which is here. And you need to also add a 1% dealer's freight, whatever that is, right? And then this is the total purchasing price for the car, right? And you need a loan, as we said, 8.5% APR over 48 months. And so let's look at what happens in this example. So don't look at the cash flow diagram for a minute because there's something that changes first. And so I know what the price of the car is. This is the invoice price. I can compute the sales tax at 4%, the dealer's freight, which is 1%. I have these numbers here, and these are all computed based on the original car price. I add them up, I get the total purchase price. Now what changed is that the guy who's buying a car says, I can actually make a down payment. Remember, down payment is muqaddam. So I can pay this amount out of my pocket right now. And so that means is that leaves $20,000, which is going to be financed, right? This is, the guy is going to get a loan for this amount. And here we have the interest rate from the dealer. Well, yeah, I said it was a bank. It was actually the dealer who financed the car, so 8.5% APR. And this is going to be over 48 months. And we actually need to find A. So A, so the loan is going to be paid in equal installments, which is kind of like the default option for loans, right? You always pay back equal installments. And we need to find what is each payment, basically, A. So you see here, I'm only taking out a loan for the $20,000. So that's why this arrow here is not the purchase price of the car, but it's only the amount that is left and needs to be loaned. And then I make 48 payments. So the first thing I need to do in order to find A, well, I have what P is, right? So I have my P, which is here, right? So I can use the formula for A given P. What I'm missing is my I and my N. And that's what you need to compute, and that's what these steps were telling you to do, right? Compute your I and compute your N. And so let's go over these steps and see what happens. So this is, again, the same cash flow diagram. Notice that the payment period is per month because you're paying back the loan in months. The question actually does not say what the interest period is. But the book says by default, whenever you have a car loan, an auto loan, it's always going to be per month. That's just common. So if you don't hear, like if the question doesn't say anything and the question is about a car loan, always assume that the interest period is per month, unless the question says otherwise. Okay, so here this is the case where they both coincide. My payment period is equal to my interest period, and they're all in months. So this is the case where C is equal to 1. And so I'm given P, I'm given R. Well, K is the number of payment periods per year. So per year, there are 12 months. I'm paying every month, so there are 12 payments per year. N, so remember, N is the total number, right? So you take however payment periods you have in a year, and then you apply, then you multiply by the number of years. And I think actually to be more accurate, was it K times? It's actually M, right? So in general it's M, but in this case M is equal to K because C is 1. So in this case it's either K or M multiplied by the number of years. It doesn't matter. Okay. And C is 1, as we said, because they coincide. I need to find A. So first I compute M. C is 1, so M is just equal, which is 12. I take my APR, I divide by 12. So I find my effective interest rate per month, which is this thing here, the 0.7%. And then I compute N, which is just the total number of payments. And if you see here, I have 12 payments, but really it's over 4 years. So 12 times 4 is 48, which is exactly how many arrows that I have, how many payments. And then I plug in the formula like I did before. But now, of course, I use this correct I here. So I don't use the I that was given here, which is really R. I don't use 8.5%. I use this I, and I use the correct N. And I apply the formula same as before, and I get my answer. All right? So now the question, like this example, makes a little bit of a twist and says, what happens if you pay 25 installments, right? So you make 25 payments, but then immediately after the 25th payment, you actually want to pay off the remainder of the loan, right? So you don't want to continue paying the loan for 48 months. You just want to make 25 payments, and then you want to pay the remaining balance immediately at 25. So this is what this looks like. So here is the original cash flow diagram, this whole thing. And here, in this case, you're making 25 payments, so all the way up to 25. But then here, you actually want to pay all of this blue stuff at time period 25. So how do I find that? So you guys should know how to find this.
Use the present worth formula.
Yes. So I need to find P given A. And notice, remember what we said about equal payment series? If I find P is going to be one time period before the first payment, which is exactly what I want, right? So it's one time period before 26. And so it's going to be here, which is perfect. Of course, I need to find I and N. Well, I already did in this case, because this is just the same as the previous example. I mean, it's really just a part B to this example. So I use the values that I computed. Oh, of course, sorry, that was a big mistake. So I is the same, right? But N is not, because N relates to the number of payments. And so here I have 23 remaining payments, right? So don't use 48 in this case, use the 23, which is how many equal payment series do you want to find the present worth for, right? And then you compute and you find this value, right? So hopefully this is starting to make sense to you now. You know what effective is, and you know what the nominal is. We're going to look very briefly at case 2 at the start of next class after the quiz. And it's very similar, really. I don't see much of a difference, except C is not equal to 1. But if you have the formulas, you can figure it out. We're going to see some examples, and then we're going to talk about debt management in the second half of the lecture. And so we'll stop here. If there are no more questions, so let me stop recording. I will see you guys on Tuesday. Please make sure to be on time for the quiz. Otherwise, if you have questions, you can either ask me now or in the office hours. So see you guys in 2 days.